learned so far, that qualifies you to accept positions, and you'll be thought, in fact, for positions in the nuclear industry. However, all of us must learn about how to protect ourselves against radiation. So if we share the screen, now we find ourselves going to the chapter on the units that are used in measuring radiation, and then study its effect on the human body and how to protect ourselves, our co-workers, and in general, members of the public. So I'm going to go to the chapter on ionizing radiation units and standards. We already have learned to a certain degree about radiation when we dealt with gamma radiation and how to detect it, and we covered the laws of radioactive decay. But radiation can have beneficial effects in industry and in nuclear medicine, but it also can affect the human body in that radiation can affect the genes on the chromosomes, the strands of the chromosomes inside the cell of the nuclei in the human body, and plants, in fact, too. So it's a topic that is first ubiquitous in the sense that radiation is around us, and we cannot simply avoid dealing with it. And if we deal with it in a safe way, that would be like electricity. It can harm us, but it can also do, is doing, in fact, very good contributions to human technology in general. We have to understand that the term radiation is used in a broad sense. It encompasses photons in the electromagnetic field, one of the forces of nature, such as visible light, microwaves, radio waves, X-rays, and gamma rays. Our interest is in X-rays and gamma rays. We leave the radio waves to the electrical engineers as well as the microwaves. However, it also encompasses other particles, particles that have very, very high energy that comes to us from other parts of the universe, and we call them cosmic rays. Electrons from radioactivity, alpha particles from radioactivity are also particulate forms of radiation. When we deal with radiation, we here mean ionizing radiation, radiation that has enough energy to ionize the atoms, in the sense that ionization means that it splits an electron from the atom, the neutral atom, and it becomes an ion in that case. This is a common screen that shows us the different radiations that people have to deal with. And on the left scale, this is the length of the radiation in centimeters. So you can find very long wave radiation. That would be electric power generation. And if you go to short wave radiation, you can get all the way to cosmic radiation. Look at how many orders of magnitude that is. That's 9 and minus 12. That's 21 orders of magnitude in the range. The visible part of the spectrum that we can see is a very, very narrow part, as you could see here, around a little above 10 to minus 4 centimeter in wavelengths. Above the visible range, we have the ultraviolet. Interesting enough, we humans cannot see the ultraviolet, but some animals like bees can see the ultraviolet. Hence, they can see the position of the sun across the clouds, but humans can't, and it affects us. It can burn our skin. If you're not careful, even on a cloudy day, you can get your skin affected by the ultraviolet. On the other side of the visible spectrum, we have the infrared, which is heat. And sensors in our skin can sense heat, obviously. So we have a range a little beyond the visible light that affects us, the ultraviolet and the infrared. The shorter the wavelengths of the radiation here, you'll find that the higher the energy on the right scale. So here you could see the light scale is the energy in electron volt. In electrical power, the photon energy is 10 to minus 13 electron volt. Radio, television, and radar is 10 to minus 4 electron volt. And in the visible region is in the range of 1 to 10 electron volt, maybe a few electron volts. That energy range is not sufficient to ionize the atoms, meaning split them of their electrons through processes that we have studied, the Compton scattering, the photoelectric effect, and pair production. But when you get to the range of the X-rays and the gamma rays, definitely the energy is enough now. It's in the million electron volt here. If you take 10 to the 5th, 10 to the 6th is here in the million electron volt, and even in the kilo electron volt range, radiation can have ionizing effects. So in that case, the atom, the neutral atom, is destroyed by ionizing it, having an electron split out of it. And in that case, there is biological damage. Lately, in the range of the microwaves, there have been effects being discovered through, we are using microwaves in our phones, in our computers, in our watches, but radiation in that case is designated as non-ionizing radiation. I'll devote a chapter after the ionizing radiation to non-ionizing radiation because there have been discovered some effects from the very widespread use of microwaves in our domestic devices, phones, and computers, and so on. All right, so radiation is important, and as I suggested, we are worried about ionizing radiation, radiation that has enough energy to ionize the atom. There are two types of ionizing radiation if we classify them. One type we call directly ionizing radiation, and this form of radiation can eject orbital electrons directly from the atoms through interacting with the Coulomb force of the atom. And these include charged particles such as electrons, protons, and alpha particles. They're charged, so the charge on them interacts with the Coulomb energy that keeps the electrons around the nucleus of the atom. Indirectly ionizing radiation, these are forms of radiation that indirectly transfer energy to charged particles of the absorber atom, such as the electrons or protons. And in that case, these include neutrons. Notice that neutrons are neutral, so they do not interact with the Coulomb field around the nucleus, as well as gamma rays. They're also neutral, but they can eject the electrons. So this is indirect ionization, whereas charged particles in general, electrons, are directly ionizing. We can show this on that diagram where high energy, say neutron, can go through the electronic cloud around the atom, not cause any kind of interactions, but then it hits, if it hits the nucleus, then you get basically intense radiation. You'll find that it can start the ionization process. All right, so we have already in the chapter on radioactivity defined the unit of activity to measure the interaction of radiation with matter. And the unit that we came up with is in the SI system of units, the Système International, the Becquerel, honoring Henri Becquerel, the French scientist who discovered radioactivity. 1 becquerel is abbreviated as BQ, and it is really 1 disintegrations per second. Some people call it 1 transformation per second. In the conventional system of units, the unit is the Curie. in honor of Marie and Pierre Curie, who did research on radioactivity, particularly on the ores of uranium, where they discovered, Marie and Pierre Curie, they discovered two new elements, radium as well as polonium, named after the native country of Marie Curie, who was born in Poland but lived in France. 1 Curie is defined as the activity of 1 gram of the radium-226 isotope that Marie and Pierre Curie discovered. So if you take 1 gram and estimate the activity of 1 gram of the radium-226 isotope, I can give you this as an interesting problem. You'll find that it has an activity of 3.7 to the 10th disintegrations per second. So 1 Curie in that case is 3.7 to the 10th becquerels. All right. So and if you reverse it, 1 becquerel is 27 10 to the minus 12 Curie. So becquerel is a small unit for small amounts of activity. The Curie is one for the large amounts of radioactivity. They are interchangeably used in the fields. So I'll find you a way later on that we can relate the becquerel to the Curie. In fact, we'll find that as we go along, I'll define them in both ways, and we'll see how it becomes more meaningful in general. The interaction of radiation, again, with matter differs according to the nature of the radioactivity. So if you have X-rays or neutrons, when they attenuate or lose their energy in human tissue, you find that they decay in a way that is more or less linear. However, if you deal with ionized particles like a proton that has a charge or a nucleus of neon, you find that they lose their energy in a different way and deposit their energy at the very end of their path in the tissue. So these protons and neon nuclei would be very good to kill a tumor, and they are used in nuclear medicine to kill soft tissue tumors, especially in the brain. They can penetrate into the tissue to a distance of 15 centimeters, and with neutrons and X-rays, they are depositing their charge as they are penetrating our tissue. So the judicious use of radiation can be used beneficially for different applications in general. Now, as radiation interacts with air, as we said, it can cause ionization. So in that case, if you are in a location where there is radiation, the air gets ionized. And in that case, we are going to define another unit that describes to us the degree of ionization. And it can be measured very easily with a gold leaf electroscope that you may have learned about. And the same idea is used in dosimeters to measure the amount of radiation that humans are exposed to in a radiation environment. This radioactivity, as we know, is extremely ubiquitous. It's all the way around us. It's also in our own human body. So we discover that, for instance, for an adult human person of 70 kilograms in weight, you'll find that each kilogram of our weight contains about 100 becquerel of radioactive materials. It could be potassium 40, it could be some strontium 90, it could be carbon 14, a whole list of them that I'll show you in a moment. And in that case, each one of us has 7,000 disintegrations per second occurring in our body. So you can say that as humans, we are to a certain degree radioactive. Any materials that we use in human activities somehow contain some level of radioactivity. And the question here is how much is too much so that we can protect ourselves against any possible deleterious effects that we'll also study. For instance, if you have a can of coffee, 1 kilogram, it has 1,000 becquerel of activity or disintegrations per second. And the more solids you have in materials, the higher the level of radioactivity in them. Superphosphate fertilizers contain traces of uranium and its decay chain daughters such as radium as well as thorium. And you find that it has the same level of radioactivity as the human body, about 5,000 becquerel or 5,000 disintegrations per second. Even the air in a typical home, 100-meter square home, would have 3,000 to 30,000 becquerel just in the air from a gas that we designated as a daughter in the uranium decay chain. And at room temperature, the radon gas has a very low boiling point, so it is emitted as a gas. In a typical home, we have the air basically containing 33,000 to 30,000 disintegration per second. And we breathe that air, by the way. Radon is as we know, an inert gas or a noble gas like helium or like neon. It does not interact with the chemistry of our body, but it decays into another two isotopes, polonium-210 and lead-210, and these are solids, and they can deposit themselves on the alveoli inside the lung, emit alpha radiation, and that alpha radiation can cause tumors in our lungs, especially among smokers who get smoke or particulate matter from smoking cigarettes deposited in their lungs. Household smoke detectors use a circuit that is connected when there is smoke in between two electrodes and warn us about fires or smoke, say, emitted in a kitchen. They use in the United States the isotope americium-241. It's an alpha emitter. This one has 30,000 disintegration per second or 30,000 becquerel of activity. So if you have a household smoke detector, you know it's a lifesaver. The smoke detectors gave warnings and saved hundreds of thousands of lives, but do not position your smoke detector in an area with high traffic, like in your kitchen or on your bed. And when a smoke detector reaches its end of life, it has to be disposed of in a judicious way, not in common landfills. In medical diagnosis, to detect the presence of disease, radioisotopes have saved hundreds of thousands of lives. You'll find that we're talking now about 70 million becquerel. Look at this, it's 3 orders of magnitude more than what we have in our human body. And now if you go to therapy, we're using the radiation, say, to kill a tumor, we are going another 7 orders of magnitude in the activity. So in that case, radiation can cure our diseases in the field of nuclear medicine. Of course, we are generating waste from the fissioning of uranium, and we have to dispose of it. And one way of disposing of the waste is to incorporate it in glass. And we know that glass has lasted since olden times without much leaching of the minerals in it. So in that case, vitrified means it is glassified, let's say, classified nuclear waste. We are at the same level as activity of a radioisotope source for the medical therapy or the treatment of diseases in general. Interestingly enough, a freshly separated pure uranium does not contain the daughters of the uranium, so its activity is very low, 25, say, million becquerel. But as it ages, the daughters of the uranium and the isotopes like radium and radon and so on form, and its activity becomes quite high over time. That would be the same as the ore that we get of uranium from, say, Canada. They are at the same level as a freshly separated and manufactured pure uranium. If that uranium ages, then you find that its activity increases because of the generation of the daughter products like radium-226 in the material itself. You find that the different parts of the world have different concentration of uranium in the ore. So in Australia, it would be maybe 100 times less than the ore from Canada, which is much more highly concentrated. Low-level waste is waste generated in the production of nuclear power, like waste clothing and oil drippings from engines and so on, as well as waste from the field of nuclear medicine when radioisotopes are used. This would be 1 million becquerel of activity. Interestingly enough, burning coal, as we know, is an open system. So the ash from burning coal is spread or diluted into the atmosphere of the Earth. Why? Because there is so much of it that you cannot really isolate it like we isolate the fission products from a uranium nuclear power in a nuclear power plant. So you find that as we burn coal, we are releasing radioactivity to the atmosphere. If you take 1 kilogram only, it has 2,000 becquerel of radioactivity. Let's compare this to what's in the human body. So each kilogram of coal releases almost 1/2 the radioactivity in the human body to the atmosphere. Granite that people use as kitchen tabletops and in construction, in architecture, for instance, if you go to Central Station in New York, they have lots of granite. Granite contains substantial amounts of uranium as well as thorium, and then they decay, and you'll find that the activity there is 1,000 becquerel. So it's all the way around us. It's part of our life. It's in our human body. We go back to the concept of exposure. We said that radiation in air, not in a material, in air causes ionization. And we measure that ionization in terms of the charge in coulombs that is created in 1 kilogram of air. So we define a new unit for measuring radiation here, just in air, as X, the delta Q, the change in the charge per unit mass of the material. And we have a unit in that case in honor of the gentleman who discovered X-rays. That's Mr. Rontgen in Germany. And the Rontgen is, by definition, 2.58 × 10⁻⁴ coulomb of charge per kilogram. That's in the SI system of units. If you translate that to the conventional system of unit, you'll find that we can describe it in terms of the ESU, or electrostatic standard unit, electrostatic unit ESU. That's what 3.3 × 10⁻10 coulomb. For small magnitudes of exposure in the air or the ionization, you find that we use the Millirantagen, which is 1/1000th of a Rontgen. A simple way of remembering what it is, you'll find that the Rontgen is the amount of exposure to radiation that leads to the generation of 1 electrostatic unit of charge in 0.001 grams of air at standard temperature and pressure. So if you take 1 centimeter cube of air at atmospheric pressure and 0 degrees Celsius, you generate 1 electrostatic unit, which is 3 × 10⁻10 coulomb. Some radiation detectors would give you the measurement of the exposure in the air just directly in Rontgen, and the radiation, in fact, can cause a tremendous amount of ionization in air. So let's take an example here. So if you have a detector and you're close to a source of radiation, and the detector tells you, oh, the radiation exposure or the ionization is air is 1 millirantagen per hour from a gamma rays from a source of radiation, we can calculate that 1 millirantagen per hour you can turn the millirantagen into rantagen per hour, change the hour into second, so it becomes now hours per second. Change the the rantagen into charge created per kilogram. That's what we said, as we said, 2.58 10 to the minus 4 coulomb per kilogram per rantagen. So rantagen and rantagen cancel. We are left with coulomb per kilogram per second. And we know that the coulomb is a charge of the electron, and that constitutes really also the charge of an ion. So that's 1.6 10 to the minus 19 coulomb. So that coulomb per kilogram creates a number 10 to the 19 here in the numerator of ions in the air, and that's per kilogram. Let's turn it per gram, and we said that that creates a charge of 0.0012.93 grams per centimeter of cube of air. That's a weight of 1 centimeter cube of air. The units cancel, the numbers cancel, and we find that 1 millirantagen per hour can create in 1 centimeter cube, just a little tiny 1 centimeter cube between our fingers, about 600 ions per centimeter cube per second. So you could see that the radiation can be extremely ionizing in air. So here we defined ourselves another unit for measuring radiation when we are dealing with radiation surrounded by air in general. We already dealt with the absorbed dose unit, which we designated as RAD, the radiation absorbed dose, when we dealt with the preservation of food by radiation chapter, as well as the sterilization of medical products. We defined the RAD as the radiation absorbed dose of the absorption in any material. I repeat here, any material of 100 ergs per gram. That is in the conventional system of units, a centimeter, gram, second. And that is the same as 0.01 joule per kilogram. You know that 1 joule is 10 to the 7th or 10 million ergs in energy. That unit is very large, so we use a millirad as 1/1000th of a rad. That is in the conventional system of units, and in the SI system of unit, we honor a gentleman, Mr. Gray there, who did research in radiation. And the gray is the unit of the absorbed dose in the SI system of units. And that corresponds to 1 joule per kilogram. So joule and kilogram are units in the MKS, or meter kilogram second, or what we call today the SI system of units. The interesting thing is that 1 gray is equal to 100 rads. So we can say that 1 centigrade is 1/100th of a grad, like centimeter. Remember, centi is the prefix that designates 1/100th, and 1 milli gray would be 1,000, 10 to the minus 3 third gray. So if we are dealing with units, I like to describe them as basically that one rad is 1 centigrade, or 1/100th of a gray, and in that case we don't get confused between the units. Well, so here we have 3 units for measuring radiation: the activity, the exposure or the degree of ionization, and the radiation absorbed dose. The radiation absorbed dose does not describe any kind of biological effect of radiation. Different radiation types affect different materials when they are alive, living matter, in different ways. So in that case, we try to differentiate between the effects of radiation on different living materials, plants or animals, including humans, of course, by measuring the effect produced by some type of radiation relative to a reference. And the reference in that case is taken as X-rays or gamma rays that have an energy of 100 kilo electron volt. So it describes really how more damage or effects radiation can have. Different types of radiation can cause in different types of materials. And that ratio is designated as the relative biological effectiveness. So in that case, we now evolve the RAD unit that applies only to solids and materials that are not alive into biological matter that is alive. And you'll find that the effects of radiations from different materials differ from one type of radiation to the other. Since we took the reference as a 100 kilo electron volt X-rays, we take the round off of that radiobiological effectiveness, and we call it the quality factor. So you could see here now that it's an integer, it is not a fraction, it doesn't have a decimal point. If you use alpha particles, protons, and fast neutrons, they cause more effects or damage or beneficial, depending on the use, 10 times as much biological effects as X-rays or gamma rays of the 100 kilo electron volt range. So in fact, that case, we designate the effect, the relative effect, by what we call the quality factor. So alpha particles, protons, and fast neutrons cause 10 times the effect in biological matter of what 100 kilo electron volt X-rays would cause. If you have heavy recoil nuclei, oh, the damage is even higher. It could be 20 times as the quality factor. Neutrons, depending on their energy, can have 1 million electron volt neutrons quality factor of 11, 20 million electron volt neutrons a quality factor of 8, and thermal neutrons have a quality factor of 2. Beta particles also can have more effects if they're above 30 kilo electron volt. They have the same effect as the X-rays, but at lower energy, they cause slightly more damage. And heavy ions can cause as much damage as heavy recoil nuclei. And the quality factor here, I repeat, is a round off of that radiobiological effectiveness. How is it that RBE being determined? By experimentation? So you grow bacteria maybe in a petri dish, then you irradiate the petri dish with a type of radiation of interest, and you count how many of the cells growing in the petri dish have survived and how many did not survive. And or you can do it on mice, definitely not on humans. So animals have been used in the past, and we have good information really about how those types of radiation affect biological matter. It has to do with the linear energy transfer. As radiation is being slowed down in a biological matter, it loses energy for every little distance it travels. So it's the linear energy transfer. It's a negative factor because it's a loss, is in kilo electron volt of the energy of the particle being slowed down in a thickness dx of material in general. So in essence, different types of radiation behave in different ways. This is a picture of how alpha particles behave. That's an alpha particle source. You find that when they're emitted from a source of alpha particle, like uranium maybe, they move in straight lines. This is the alpha particles moving in a straight line. And then notice something interesting here. At the end of their path, this is in a picture in a cloud chamber. We described the cloud chamber earlier. And in that case, the tracks are like the condensation trails that happen when airplanes fly at high altitudes. So the condensation trails in the cloud chamber are shown here. They lose most of their energy near the end of their tracks. This is called the Bragg effect, in the sense that most of the energy of the alpha particle is delivered near the end of its path. You see how this is thicker than the rest of the path right here. Electrons, on the other hand, move in a different haphazard way because they interact with the electronic cloud of the atom. So if you find an electron's path in a cloud chamber, the condensation trails are erratic. They don't move in straight lines, but in the same way as alpha particle, you could see that the path becomes thicker and thicker near the end of it, so they deposit their energy eventually near the end of the path. Alpha particles can be stopped by basically a piece of paper, so the range is very short. Electrons can be stopped by some aluminum foil, so they are more penetrating than alpha particles, and of course, neutrons can penetrate even more. All right, so in that case, to be able to describe the effect of radiation on biological matter, including the effect of radiation on humans, we define what we call the effective dose. Some people like to call it the dose equivalent, and some people like to call it the biological dose. So we take, in that case, the dose that is measured as an absorbed dose in radiation absorbed dose, and multiply it by that quality factor that depends on the type of radiation and the energy of the radiation. So we define what we are going to call the effective dose as the absorbed dose in rad multiplied into the quality factor that we defined for different types of radiation. You can define also an effective dose rate by taking the rate of change dH by dt, and in that case we get a new unit. The new unit is what we call the radiation equivalent man, which is Q sub F, the quality factor multiplied into the rad or the absorbed dose. This is in the old conventional system of units. It's a large quantity, so we use a milliram, which is 1/3. However, in the SI system of units, we are replacing the rem by the sievert, another gentleman who worked in the radiation field being honored, and the 1 sievert is 100 rem. So in that case, you can say that 1 rem is 1 centisievert, or 1/100th of a sievert. And when we compare the doses of different types of radiation pretty soon, we are going to use both units so that both for the centisievert and rad, as well as the centisievert and rem, as well as gray, and the being equal to 1 rad being equal to 1/100th of a gray. In that case, we can use either system of units and be cognizant of what is going on. As I suggested, radiation is very ubiquitous in our world, and I suggested it's in the human body. We are all radioactive to a certain degree, but it's also around us in nature, and it differs from one location to the other. All of us are subjected to the natural background radiation under our feet, but also from above our head. And that would be cosmic radiation. Cosmic radiation comes to us from outer space. It comes almost isotropically hitting the Earth. So it comes from all other parts of the universe. And it can carry very, very high energy, like in the graph that I have shown you at the beginning of the lecture. Even though some alpha particles, for instance, have energies in the million electron volt, these cosmic radiation have energies coming to us from other parts of the galaxy or from our own sun with energies in the giga electron volt, meaning it's 1,000 times higher in energy. The cosmic radiation interacts with other parts of the atmosphere, generating neutrons and generating particles that are maybe 200 times the mass of the electrons. And it's a whole panoply of particles, the muons and the pions. And we could be sitting, each one of us now, watching their computer and being irradiated by what's called the cosmic ray shower. If we cover more material about space radiation, I'll show you more detail about cosmic ray shower. We also have inevitably sources of radiation in our own body. 0.01% of potassium in nature is the isotope potassium-40, and that one has a billion-year half-life. And potassium in our body is an electrolyte. It's necessary for the operation of our heart, our muscle. We cannot live with it without it. So 0.01% of it is the radioactive potassium 40. We also have carbon in our body, our organs and our skin contain carbon, and carbon 14 is a result of the interaction of this cosmic radiation with atoms of nitrogen in our atmosphere. Remember that we breathe oxygen, 15% in our atmosphere, but most of what we breathe is nitrogen, about 70% in general. So let us look at sources of radiations from different sources in general. Man-made radiation is part of our technological society, but in addition, we are subject to radiation from the rest of the universe around us. So let us consider what is now, since we have defined units, what is the level of radiation that we get from natural sources and from internal sources. External to the body, the natural sources, as I said, can be cosmic radiation. And that cosmic radiation gives us a dose equivalent or an equivalent dose in units of rem per person per year. This is what we get in rem per person per year. But we said that the rem is also 1 centisievert. So in that case, the units are the same. From cosmic radiation, let's turn it into millirem. 50 millirem per person per year is what we get from cosmic radiation. From Earth materials like uranium and radium-230, 226, we get 47 millirem per person per year. So what we get from the Earth is almost equal to what we get from outer space. And building materials contain traces of thorium and uranium and their daughter products like radium-226. We get a tiny amount of 3 millirem per person per year. Now, remember that we also have sources in our body. These 3 sources here are external to the body. These are 2 sources internal to the body. Air inhalation would be the inhalation of radon, the radon isotopes 220 coming from the decay of thorium, and the radon 222, which results from the decay of uranium 238. And that would be primarily from the building material. So that is a small amount, 5 millirem per person per year. But in our own body, element naturally occurring in tissue in our own body, we have, as I mentioned, the potassium 40 typically, as well as the carbon 14. We get 21 millirem per person per year. So we can say that from the natural sources, a number to remember so that we can make a comparison later on. If you add the radiation external to the body and radiation that comes from internal sources, each one of us is getting 126 millirem per person per year. And that's a natural environment. Humans and plants have evolved in the radiation environment. However, we are living in a technological society, and our technological society has discovered radioactivity and found uses for them, or have devices that generate radiation like TVs and computer screens. For instance, we use electrons. The electrons, as they slow down, they generate the Bremsstrahlung. This is a form of X-rays affecting our eyes and our brain and our faces when we use computers, for instance, or if you watch TV from a close distance. So we have man-made sources, and it's worthwhile to compare how much is the dose of radiation or the dose equivalent that we get from man-made sources. On average, each American gets from diagnostic X-rays, if say they affect their bones playing sports, spraining a foot, you worry about it's having a broken bone, so we subject ourselves to X-rays, and that diagnostic X-rays gives the average person in the United States 50 millirem per person per year. Radiotherapy now curing disease with radioactive isotopes or radiotherapy X-rays, we get on the average 10 milliramp per person per year. And if it's internal diagnosis using radioactive isotopes, on average, we get only 1 milliramp per person per year. So if you add up the subtotal from the uses artificial sources of radiation, it can add up to 61 milliramp per person per year. Let's compare this to what we get from nature. It's 126 milliramp per person per year. So our technological society has added 1/2 the amount of dose of radiation that we get from nature. If you think about the atomic industries, the generation of nuclear power in industry, laboratories, in universities, and so on, the amount of radiation that we get, or dose of radiation, is 0.2 milliramp per person per year. Watching television, computer screens, industrial waste gives us 2 milliramp per person per year. And interesting enough, in the 1950s, countries were testing nuclear weapons in the atmosphere. And as a result of testing the nuclear weapons, lots of radiation has been injected to the upper atmosphere, especially the upper hemisphere of the Earth. And that radiation is still falling down back to Earth. So each one of us has some radiation from that radiation that was injected into the atmosphere in the 1950s, and particularly the isotope strontium-90 efficient product. You'll find that this contributes 4 milliramp per person per year for each one of us. So the total man-made sources, in fact, is 67 milliramp per person per year, still 1/2 of what we get from the natural radiation environment. I'll try to have you remember, the natural radiation environment is 126 milliramp per person per year. The man-made sources give us 67 milliramp per person per year. If you add the two, each one of us, natural and man-made radiation, received on average 193 milliramp per person per year. Notice that I use the unit of the milliramp because it's easier to use than using the millisievert or the sievert in general. All right, so we have the radiation around us and we know how to measure it. We have very sensitive instrumentation, electronic instrumentation, developed by our wonderful electrical engineers for us to measure radiation to the level of the number of atoms even in the human body, say in a whole body counter that people use in the nuclear industry. You can count how many atoms of radiation are in a person's body. So how do we protect ourselves against high levels of radiation? It's very important for anybody who is chooses to work in the nuclear industry. First, obviously, an obvious reason is to protect themselves. But engineers are learned people, so they also are responsible professionally and ethically to protect their co-workers, people who may not know as much about radiation as engineers or scientists do. So, and of course, in addition, there is another professional ethic there to protect the society at large and members of the public. So how do we protect against radiation? There are obvious ways to protect against radiation. The first, well, we said that we have ways of detecting either the activity or the exposure or and measuring the effective or dose equivalent. To protect against radiation, we follow several principles. We limit the time of exposure to radiation. Sometimes, for instance, X-ray technicians in hospitals or medical doctors working with in nuclear medicine with radioactive isotopes basically can protect their patients and themselves by limiting the number, say, of X-rays in dental X-rays, which is not unfortunately followed by every person there, but limiting the time over which people are exposed to radiation. Instead of taking 10 X-rays, for instance, they can only take one and gain the same amount of information that is needed from the X-rays. If there is a source of radiation, you can limit the exposure by keeping a distance from the source of radiation, because we know from our chapter on the non-multiplying media as well as the multiplying media that the distance, the inverse square law, works for radiation too. So if you have a neutron source in a part of a building, you isolate it and limit the access, the distance from the source. And the third aspect of protection against radiation is obviously shielding against radiation. You create a material that would shield the person or the living creature away from the radiation source. And we know already that to protect against gamma radiation and X-rays, we use material that contain lots of electrons, like steel, iron, or lead, or even uranium. If you want to shield against neutrons, you use materials that are rich in protons, because then the neutrons are of the same mass as the protons, and every collision with a proton by a neutron can lose its energy and reduce its effects biologically in general. And the fourth principle of protecting against radiation is containment of radiation. And this is followed, of course, in the operation of our nuclear power plants, in that we fission the uranium. And unlike coal power plants or fossil fuel power plants, the system is operated as a closed system. So the radiation is generated, but is not diluted in the environment, like, unfortunately, what is done today with the burning of coal. And coal, as I mentioned, itself contains radioactivity in a ubiquitous way too. So what are the sources of radiation exposure? Of course, any release of radioactive material is a potential source of radiation exposure to the whole population. And we suggested that the average person in the United States is exposed to an effective dose equivalent of about 360 centisievert or rem, or you can say 360 millirem, thousands of rem of whole body exposure per year from all sources. The per capita yearly gonads, which are really the organs, reproductive organs in the human body that are mostly affected by radiation, is from the table 4, 193 millirem per person per year. What are the consequences of exposure? Unfortunately, we learn about the consequences of exposure to radiation from accidents that happened in the field and from the survivors of the nuclear bombings in Japan, in Hiroshima and Nagasaki, particularly in that case for the gamma and neutron radiation in general. Small doses of radiation can cause some harm, but the body is able to recover from radiation. In fact, some people suggest that small doses of radiation may be beneficial to animals and humans, in that they excite our immune system to renew the damage that is caused by the radiation. But large doses of radiation overwhelm the natural defenses of our immune system, and in that case, they can be quite harmful to our body. So the question now is to figure out how much is too much to protect ourselves against radiation in general. Two forms of radiation exposure exist. Chronic exposure, this would be continuous, and these include can cause genetic effects such as cancer, precancerous lesions, benign tumors, cataracts in the eyes, skin changes, and congenital defects. Acute exposure is that is over a long period of time. Maybe somebody living in an area, in a mountainous area that has granite rock, and the granite, as we know, contains sources of thorium and uranium and their daughter products. The acute exposure is different. In that case, it would be exposure to a large single dose of radiation, for instance, working in a nuclear submarine and having to deal with a valve that is not operating as to specifications. A person can get some large dose of radiation. So what are the effects that we know about the effects of radiation? So these are the observed effects of radiation. If the effective dose or the dose equivalent is larger or equal to 1,000 rem, or the rem, as we said, is centisievert. So centisievert in the SI system, rem in the conventional system, you'll find that at the 1,000 level, these were doses that the firefighters at Chernobyl fighting the fires in the reactor were exposed to. At 10 sievert, basically a whole body dose would cause just not 1,000, but even a 10 sievert, you'll find that you get what's called radiation sickness in that case. Radiation sickness is nausea, decreased white blood cell count, because the radiation can kill the cells that produce the white blood cells in our spine, and 10 sieverts can cause death within a few weeks. Between 2 and 10 sieverts in a short-term dose can cause severe radiation sickness by increasing the likelihood that it could be fatal. That level of radiation is the goal of the weapon that's called the neutron bomb. So in that case, the device is built up to generate primarily neutrons that can penetrate fortifications or even the walls of tanks, and in that case, incapacitate very quickly the persons who are shielded in those enclosures in general. 1 sievert in a short-term dose is the threshold for causing immediate effects of radiation. And the radiation, as I said, would inhibit the production of the red blood cells in our spine. So our immune system cannot fight bacteria. Radiation also can affect the lining of our gastrointestinal tract, the stomach. And we know that our gastrointestinal tract is full of bacteria. What are they doing there? Oh, they're disassembling the food that we eat into its original components so that the body can absorb them. So if the lining of the stomach is affected, you find that, of course, those bacteria invade the rest of the body. One of the symptoms would be severe diarrhea. So the neutron bomb would totally disable any combatant without destroying the equipment or the fortifications where they are. So hopefully it will not be used in our existing situation on the world where we are living under the threat of nuclear war. Above 10 centisievert, the probability of cancer rather than the severity of illness increases with the dose. And the effects will not show up immediately because the cancer cells start multiplying, and the multiplication effect forming a tumor does not appear until several years later. So the estimated risk of a fatal cancer is 5 of every 100 persons exposed to a dose of 100 centisievert. If the normal incidence of fatal cancers were 25%, you'll find that this increases to 30%. 5 centisievert, interesting enough, is 5 millirem is the lowest dose that the body can expose to without causing much harm. The body can recover. And we do not observe any evidence of cancer being caused in adults if the dose is in the range of the 5 centisievert. And that affects really the criteria that we use in terms of exposure to radiation to humans. Notice that, again, if you look at our table, 5 is a very small fraction of the 1,000 rem of radiation that would cause a fatal effect. So 5 centisievert is, or 5 millirem is considered a very small dose that doesn't cause much harm. Those rates greater than 5 centisievert per year can be caused by natural radiation background in several parts of the world where the geography basically has a large material that are radioactive in nature. For instance, the black sands on the beaches of Brazil that people seek, in fact, they bury their feet in it, thinking that that radiation would affect their arthritis or rheumatism, as they call it. These people are being exposed to large doses of radiation in that case. So in that case, since we know about the effects of radiation, remember 5 centisievert is the limit at which we cannot see any harm to the human body. So we have set up allowable limits for how much radiation we are allowed workers in the field that use radiation, members of the public, and professionally and ethically, if you are in a position of responsibility, that would be not your co-workers to be exposed to. 2 centisievert per person per year is the level that is totally allowable average over a 5-year period. So this is a number to remember here. This is a limit for radiological personnel, such as employees in the nuclear industry, uranium and mineral sands miners in the fertilizer industry. Fertilizers contain sources of uranium and thorium. Hospital workers who basically use X-rays. I myself had several X-rays in the last months because I had a broken toe. So in that case, we had to use the X-rays. These are have to be closely monitored. 1 centisievert per person per year is the maximum actual dose received by a uranium miner with good ventilation of the shafts of the uranium mine if it is underground. Actually, above ground, miners receive a lower dose, 0.3 to 0.5 millirem per person per year. 0.3 or 300 millirem per person per year is what we get from natural sources with an average of about 200 millirem per person per year from radon gas. The radon gas is a product of the decay in the uranium and the thorium radioactive chains. A 0.005 millirem per person per year is a small fraction of the natural radiation background, is used as a design target for maximum radiation at the perimeter fence of a nuclear electricity generating station. In practice, the dose is even less, but this is considered as the upper limit. So dealing with radiation and protection against radiation is, as I said, a field by itself that we use to protect against radiation. And the main standards that exist are implemented by international bodies. And one of them is the International Commission on Radiological Protection, ICRP. It has publications that tell us what are the allowable doses in different circumstances that should be used to limit exposure radiation. The key considerations behind the ICRP recommendation are first, justification. No practice should be adopted unless its introduction produces a positive net benefit. You have to optimize the exposure to radiation. All exposure should be kept as low as reasonably achievable. And let's remember that terminology here, as low as reasonably achievable can be the basis of an acronym, ALARA, A-L-A-R-A, ALARA is a principle for the exposure of radiation. We do not expose ourselves or other people to radiation unless the exposure is reasonably as low as reasonably achievable. And we have to limit radiation in any way. So if there is no need to get exposed to radiation, no benefit to be obtained from it, then we should not exceed the limits recommended for the appropriate circumstances in general. The ICRP recommends for the maximum permissible dose for occupational workers is 2 centisievert or rem per year, average over 5 years for people in the profession. As I suggested, the profession would be in the medical field or in the nuclear power production field. That implies that you cannot give radiation to professional in the field of more than 10 centisievert or rem over a 5 year, with a maximum of 5 centisievert or rem in any 1 year. For the public, the exposure is only within the range of 0.1 centisievert of rem per year. Average over 5 years is the limit. And in both categories, the public and workers or professional people, the figures are over and above background levels and exclude medical exposure in that case. Other organizations that set up limits for the exposure of radiation, and as engineers, we are all bound to follow those exposure limits. We mentioned the ICRP, that's the International Commission on Radiological Protection. In the United States, the NCRP is the National Council on Radiation Protection and Measurement, the Federal Radiation Council, FRC, the Nuclear Regulatory Commission, NRC, and the Environmental Protection Agency, EPA. The rules and and the laws that pertain to the protection against radiation are written in the Code of Federal Regulations. If you go to the main library and find your way to the reference library, you'll find that the Code of Federal Regulation is another way of saying the laws of the land. In that Code of Federal Regulation, CFR, in Title 10, Part 20, also designated as 10 CFR 20, you'll find that all these limitations in the use of radiation and how, for instance, the maximal permissible concentration of radioisotopes in different applications is used, and they have to be followed professionally, ethically, in any design, calculation, or any activity where radiation is being used. Some of the standards for limiting radiation effective doses are listed in that table here. And I would like to warn you about an error that people do not think about adequately. So please listen carefully to what I'm saying here. For occupational workers, you cannot have exceed a dose of 5 rem per person per year or centisievert per person per year. So that is set as the maximum exposure. However, the effective dose is not that 5. You do not expose people to radiation at the maximum allowable level. For routine exposure to radiation, it is average over 5 years, as I mentioned earlier, and it's only allowed for an age above 18 years of age. So if you take n minus 18, n being the age of the person, the number of his work in the workforce is multiplied by 2 rem per person per year. Average over a 5-year period is the maximum dose of radiation that an occupational worker is allowed to. Some people say, oh, occupational workers are allowed to go up to the 5 rem per person per year. This is incorrect. Unfortunately, in some reports and even some textbooks, that is not correct. Members of the public are not allowed to get more than 1/10 what the occupational workers are getting. So the 5 becomes 0.5, and the whole population on average from all sources other than medical exposure should not exceed 0.17, which is what we get from the the combination of the natural radiation environment and the medical sources. For occupational workers, radiation can affect different parts of the body differently. In the reproductive organs, the gonads, the total body, and the red bone, especially where the white blood cells are manufactured in our spine, that local exposure should not exceed 0.005 rem per person per year. The skin and bone should not exceed 30 millirem per person per year, and other internal organs 15 millirem per person per year. So please be aware that, say here, the N, the age is set here to be above the age of 18, because a person who is less than 18 years of age has the body organs are multiplying and they're growing, and growing cells are affected more by radiation than mature cells. So in addition, you'll find that so in that case, if you are age 19, average over 5 years, you have to say 28, then over 5 years, you cannot receive a cumulative dose more than 20 centisievert per person per year. So I repeat here again and again, the value of 2 is used here for the averaging process rather than the 5 that is incorrectly used in some publications. Not all publications, most publications are reporting it correctly, but some take the 5 value, whereas the ICRP tells us it should be the 2 value in general. There are effects of radiation over large populations like in Brazil or in Ceylon, where actually in Egypt, in northern Egypt, sediments of the Nile contain large amounts of thorium and uranium, and they show up on their beaches as black sands that contain that radioactivity. So different populations can absorb different levels of radiation. So we talk about the population effective dose as the integral of the dose over the whole population. So in that case, if the population number in terms of dose is the integral of N of HDH, the population effective dose is the dose given to the population H multiplied by that integral of the population in general. And we can set that as an example. If you have a population of 2 million people, half of them receiving 100 millirem and the other half receiving 200 millirem, you can calculate an average radiation dose of the 2 million people, the 1 million receiving the 100 millirem, 100 by 10 to minus 3, plus the other group, which is receiving 200 millirem. So you find that on average, the whole population is receiving 3,000 person sievert of population dose in general. This is an interesting table that allows an individual, and you can maybe show it to some of your friends, to calculate how much of a dose of radiation they receive per year, and to compare it to the average that the whole population is getting. As you suggest in that table here, it depends on where you live, what you eat, drink, and breathe, how you live in general. So where you live depends on the location. At sea level, the annual dose in millirems per person per year is 44. That's a dose equivalent, of course, 44 millirem per person per year. Now, if you go up to a higher elevation, you do not benefit from the atmosphere protecting you against solar radiation from our sun, the solar wind, as well as from cosmic radiation. So it turns out that at coastal cities of the world, if you are in New York, for instance, you get 44 millirem per year. But if you live at a higher elevation, like if you live in Denver, Colorado, if you go there to their state capital and climb up the steps, one of the steps is designated as 1 mile of height above sea level. So in that case, Denver, Colorado is named the 1 mile high city. In that case, you find that you get a much higher radiation dose. So for each 100 feet of elevation, the protection from the Earth atmosphere decreases. So if we are here in Champaign-Urbana and we say that we are at an elevation of 700 feet above sea level, then you add 7 millirem or 51 millirem per person per year, because we don't have that extra 700 feet of protection. If you are at Chicago, it's 575 feet above sea level. Atlanta, higher, 1,000. Dallas, Denver, as I suggested, is 5,280. That's 1 mile high city. So the less protection from the atmosphere, the higher the radiation dose that you will be getting. So let's take Champaign-Urbana as to the best of my knowledge. It's about 700 feet above sea level. Notice related to that topic is what happens to airline pilots, since they fly airplanes as their profession, and they don't have the protection of the atmosphere. Definitely, each flight that they do exposes them to some level of radiation. In Europe, flight attendants who are pregnant are not allowed to fly at all. In the United States, that is not the case. And the reason is, again, as I said, as growing tissue is more susceptible to radiation damage, and the babies in the formation stage should not be allowed to cosmic radiation for flight attendants in general. Okay, so that is where we live, the location. The type of house or the type of lodging that we use contains different levels of radiation. You notice that a stone or a brick house contains primarily materials that contain radioactivity from the thorium as well as the uranium daughters in the environment. So if you live in a brick or a stone house, you get 45 to 50 millirem per person per year. If you live in a wood house, that doesn't save you because the wood contains, we know, the isotope carbon-14 that results from the interaction of cosmic rays, neutrons generated from cosmic rays with the nitrogen and oxygen in the atmosphere in general. So if you, and you also get not just from the construction material, you get a dose from the ground. The ground, if you just walk outside in your garden, you'll find that you are getting 15 millirem per person per year, depending on the time that you spend outdoors. What you eat, drink, and breathe from food, water, and air, on the average, each one of us gets 25 millirem per person per year in the United States. As I suggested, the weapons fallout from the 1950s is still occurring. That's why nuclear testing has been banned after people discovered that they are really irradiating the whole environment. Gives us still 4 millirem per person per year. How we live, if you are physically active, you are a sport active person, you'll find that you may end up spraining a foot or breaking a foot or breaking a toe. And depending on the number of x-rays you get, the average is 10 millirem per x-ray. So if you have one x-ray, that's 10 millirem here. If you have problems with your gastrointestinal tract, each x-ray gives you more radiation than just a chest x-rays or a bone x-ray. Each x-ray gets you 500 millirem per person per year. That includes, by the way, dental x-rays, which in fact are used to an excess. So if with your dentist, request that he doesn't get too many pictures of your teeth, because you are very close to very sensitive organs the eyes, the ears, and the brain, obviously here. The average person in the United States gets about 100 milliram per person for X-ray diagnosis. And they suggested jet plane travel. You lose the protection of the atmosphere, and each jet plane travel for 1,500 miles gives you an extra 1 millirem. And if you still view the TVs, do it from a distance, because the number of hours of TV viewing gives you 0.15 milliram per person per year per hour of watching. And that's why it's a good idea to stay away from TV. In the old screens, the glass screens, you know that we have a beam of electrons that interacts with the glass. Electrons are slowed down. As they slow down, they emit what's called the Bremsstrahlung radiation, which is a form of X-rays. So we are exposed to the X-rays from the beam of electrons. We are also exposed now with the new TVs that use LEDs or liquid LCDs, liquid crystal displays, including laptop computers. The phosphors, the color phosphors there are activated by a tiny amount of tritium. Tritium does not emit gamma rays, so no worry from the tritium itself, but it emits electrons, and the electrons again interact with matter, generating a Bremsstrahlung or X-rays. So we have a small dose of X-rays even from our screen computers, from the liquid crystal displays on our phones, by the way, too, on our watches and whatever. How close you live to a nuclear power plant? Of course, nuclear power plants, as we said, are built in some kind of remote locations. If you live at the site boundary, per hours per day, you get 0.2 millirem. If you are 1 mile away, you get 0.002 1/100th amount. If you live 5 miles away, you get another 1/10th of the amount. Over 5 miles away, you don't receive any dose from the vicinity of the nuclear power plant. And you can add up all this dose equivalent, you get here your annual millirem per person dose. And we suggested that the annual average is in the range of the 230 or 228 millirem per person per year. 1 millirem per person per year is equivalent to moving to an elevation of 100 feet higher and increasing your diet by 4%, or taking a 5-day vacation in the Sierra Nevada mountains in California, and for that matter also, I would say in the Rocky Mountains or in the Appalachian Mountains, Tennessee and North Carolina and so on. All right, so we know about the effects of low doses of radiation. How did we learn about these effects of radiation? Unfortunately, it was learned from the exposure of the survivors of the bombing of Hiroshima and Nagasaki. But some other accidents happened in that at some point, people like to have watches that had luminous dials, and those luminous dials would glow in the dark. They used radium-226 to do that. And there was a factory in Chicago where young ladies were painting those dials. They used paint brushes. They dipped it in paint that contains radium-226. And as they licked the brushes, of course, they got the radium-226 in their body. So we learned about the use of radiation this way. Some people also at some point at the beginning of the learning about radiation used radiation as a cure-all. So they started selling bottles that contained sodium for people to drink, as supposedly it would give them good health. In fact, it has been destroying their health. So we know about the small doses of radiations from accidental exposures to radiation. The acute doses of radiation effects are described by what's called the LD sub 50/30. LD stands for lethal dose. The 50 stands for 50% of individuals that are exposed, and the 30 within 30 days. That terminology is also used in the pharmacology for medications and also in pest control, like what is the dose that would kill, say, some insect. But for humans, it's 500 centisievert or rem for humans. So 500 centisievert would kill 50% of the exposed population within 30 days. An interesting aspect of exposure to radiation is that it is 10,000 centigrade. Now I'm not using centisievert, centigrade or rads for bacteria and adult insects. And that's why you have those movies where you get some huge insect growing and invading the earth. Insects have the chitin shell that protects our internal organs. So in the case of nuclear war, where humans may not survive if they get doses above 500 centisievert, insects will take over our world because they can resist the effects of radiation in general. Early effects and acute effects of exposure to radiation, as I suggested, up to 50 rem, there are no observable effects really. People, the body's immune system reconstructs itself, and some people even say that low doses of radiation are beneficial in the concept of what's called hormesis, radiation hormesis. At 50 to 100 millirem or centisievert, we suggested that you get slight blood count changes. At 100 to 200, vomiting, blood changes, recovery, you can recover within weeks. But at the 200, 600, you get vomiting within 2 hours, severe blood changes, hemorrhage, infection. 20 to 100% of individual would recover within 1 month. At those effective doses of 600 to 1,000, the exposed individual will vomit, get blood changes because of the destruction of the white blood cells in the spine, hemorrhage, infection, and what you see typical when people are exposed to large doses of radiation, loss of hair. And that leads to the death of 80 to 100% of the exposed individuals within 2 months. The exposure to radiation was made other than the bombings of Hiroshima and Nagasaki and the the luminous watch dials workers was basically seen in the case of the Chernobyl accident, where heroically the firefighters helped in stopping the chain reaction. In that case, they were exposed directly to gamma radiation, but also the smoke in the fire contained fission products that were emitting beta particles. The beta particles deposited themselves on the skins and caused fourth-degree burns. So they died really of the first-degree burns. 22 individuals in the fighting of the fires of the core, which was graphite or carbon in the Chernobyl accident. And that resulted from skin burns, really. 32 individuals died from within 4 to 50 days. Third-degree burns, so 23 others, they did not get all of them skin burns, but 23 also died. Second-degree moderate, 53 individuals were exposed, and slight burns were 105. So unfortunately, the lower, of course, the burns, meaning the lower the exposure to radiation, the lower the deaths out of the exposed individuals. You could see here the 600 to 1600 rem, 21 out of 22 exposed individuals perished, 7 out of 23 for lower degree burns, and 1 out of 53 for the second degree burns. We lost 29 courageous firefighters in fighting the fires in the accident at Chernobyl. Then in that case, radiation has benefits, but also has deleterious effects. And in figure 6 here, we can show the effects that we ascribe to the dose of radiation. For an annual dose rate in millirem at 100 millirem per person per year, we consider the natural background, say 100 millirem per person per year. The cancer deaths per million individuals are shown here, like 2 deaths per individual. The slope of that curve, as you increase the exposure, you find that the cancer deaths per million person per year increases linearly. And so we can calculate from the total dose of an exposed population what would be the possibility of the cancer deaths. That's a copied graph from the report, a committee report called the BEIR report, the biological effects of ionizing radiation in general. You'll find that we assume here that the radiation dose is linear, meaning that even doses of radiation have a minimal effect. Whereas some people suggest that low doses of radiation will bring the curve down here and have a beneficial effect. I mentioned it as a hormesis effect. The best thing to explain hormesis is to cover the chapter on the ideas of hormesis in general. In essence, this is what we can learn about the dosimetry of radiation. We have now an arsenal of 4 principal quantities that we use in measuring radiation. And once you measure it, we can set up limits on what to use and what not to use. And I mentioned the ALARA principle, ALARA. This is as low as reasonably achievable exposure to radiation. Cosmic rays contribute 45 millirem to the annual per capita dose equivalent. Most of human exposure to radiation comes from the natural radiation background and the medical applications that have basically a benefit that exceeds the cost of the irradiation to exposure to radiation in general. In essence, we can say that exposure to radiation has been and will forever remain a fact of life since the beginning of life on Earth. And like we discovered radioactivity, we can deal with it in a safe way. I'll stop share temporarily. The video is not functioning. It stopped itself. But if we have any questions, I'll be happy to answer any question in the chat room before I start on another chapter. Okay, so let us deal with another important chapter here, which has to do with the we covered the ionizing radiation units and standards, and I suggested that we are also exposed to radiation that is not ionizing. And this is a new field of science that is being discovered. So I would like to cover it because it can be a lifesaver for some of you. Microwaves and lasers, of course, are forms of what we call non-ionizing radiation. They don't have enough radiation energy to ionize the particles in general. However, they have come into great use in mobile cellular phones. And as you know, our cellular phones or mobile phones are operating in the microwave part of the electromagnetic spectrum. And it's a large industry reaching the $100 billion. And people suggest we have 650 million phones sold to about 1.5 billion people. One fourth of humanity has basically is using non-ionizing radiation in the form of microwaves. I'll invite you to read it very quickly. These are sources of exposure to radio frequency radiation. Any laptop computer's screen definitely is generating microwaves. Phones, even meters that measure your electricity are emitting radiation, so that a meter reader can read it from a distance. The risk here is how does it affect younger people, and in terms of the, even though it says non-ionizing in general. Notice that radiation in the electromagnetic spectrum are photons, they're not particles. And the energy they carry is written as h nu. Nu is the speed of light divided into the wavelengths, and h, as we know, is a Planck's constant. Itself is proportional to the inverse of the wavelength. So the way shorter the wavelengths in the denominator means that nu becomes large. This means that radiation carries more energy. As I suggested, non-ionizing radiation like microwaves is not enough in magnitude to ionize atoms, but nevertheless, where does microwaves lie? It lies in the wavelengths of the 1 millimeter or the 1 centimeter. Microwaves here is below the infrared, and the visible light with all its colors that you can divide it, the violet, the blue, the green, the yellow, the orange, the red. Below the red, you find infrared, which is heat, and above the violet, you get the ultraviolet. So this is radiation, visible light, so it has less energy content. However, some people are suggesting that it may be causing effects that are being discovered depending on what uses we are using them for. So in that range of the microwaves, here is where our worry is. FM, radio, and TV, microwave ovens. If you stand next to your microwave oven, definitely you are using microwaves to cook the food. And in that case, we are exposed to it in some way. This is a bank in an apartment building. As you could see here, meters that measure the use of electricity in different parts of the building, each apartment, and all of them are wireless. They call them smart meters, and basically they use microwaves to measure the radiation. This means that the meter in your apartment, if you live in an apartment or in your home, you would have only one of these, are using microwaves being emitted in general. Microwaves are used routinely in microwave ovens, in cell phones, all of the cell phones, cordless phones also, which is a lower technology, and Wi-Fi that I bet most of you are using now, communicating with your computers in general. The way that microwaves are also used are in our phones. And this is the way our phones behave or function. The intensity, the phone is continuously locating its location by interacting with the microwave tower, especially in the 5G type of configuration. Those microwave towers are closer and closer to each other. On standby, your phone is interacting and have a low intensity of the radiation field in volts per meter. But when the phone rings, you'll find that the level of the intensity of microwave radiation rises. And when you speak, it rises even more. When you listen, it goes down. And then continuously, as you are having your phone, it is locating your location by interacting with the tower. And people have started experimenting when they found that honeybees as a biological system are escaping their beehives. So they used test hives in which they located some phone inside the hive, And over 10 days, after a few days, the workers leave the hive and do not return back. So definitely there is a biological effect that people think is affecting those bees, and the bees become the canary in the coal mine. It used to be that coal miners will take canaries in cages when they get into the coal mine to warn them about high level of methane that could kill them. So control hives had all the bees return back to the hive. So test hives with a phone left in them for 10 days had a result with what is called the colony collapse disrupting syndrome. Beehives were losing their bees. The bees got out of the hive. Somehow their system of orientation was affected by the fact that they had a phone in the hive. In the United States, the fear that microwave energy absorption, well, if it cooks food in your microwave oven, if you place your phone close to your ears, definitely it's affecting the ear, the eyes, and even the brain. So in the United States, there is a standard that we should all know about, what's called the specific absorption rate, which is the energy absorbed in joule divided by the organ mass, whether the ear, the eye, or the brain, divided by the irradiation time. So it has units of power per kilogram, or the power that the instrument is using in terms of the microwave spectrum per kilogram of the organ. And the fear, of course, is how it affects growing tissue, like in fetus, and in the case of pregnancy, this would be the exposure to the head of a baby as a fetus, or in the spectrum in general. Research has been done on the exposure of small children, which are encouraged to have phones at school to communicate with their parents. And the phone in that case is very close to their ear and their brain and their eyes. Even adults, some people carry their phone in their pockets, as you could see here, that exposes the reproductive organs and the bone marrow of the individual. So there has been some fear that basically microwave radiation can affect the human body. The Europeans have been more interested in it than the United States. In different studies in Europe, they simply detected some effects on the DNA. In Europe, in Sweden, studies, I'll invite you to read about them because of the time limit. In Norway, in Britain, they have had studies about the effects of microwave radiation. The World Health Organization, International Agency for Research, suggested that it might have an effect on cancer without really specifying that it does in general. Some private institutes have made studies also, and suggest that there may be some effect due to microwave radiation on some organs in the human body. Not only microwave radiation, but ultraviolet radiation. As a result of the COVID-19 infection in China, not in the United States, they would irradiate with the ultraviolet radiation whole buses to kill the, thinking that they killed the virus in that case. And even some dishwashers that built in China and used in China would disinfect the plates, not in the United States. Somebody should think about introducing it. Then ultraviolet also is being used. The danger or the worry is that the proliferation of these devices is affecting younger babies in general, affecting them, exposing them to microwave radiation. And there is no need for it, as some people think. Radio frequencies can cause some harm in general. And this is a critique of the use of phones. People use phones now in some kind of ubiquitous way. People walking the streets using phones in general. Some people have measured memory decreases, hyperactivity increases, anxiety and fear in adulthood in prenatally exposed mice. So experiments have been done on mice with some non-beneficial effects. Here, a report has been the first report on the effects of microwave radiation from phones in generating possible primary tumor in the breast tissue in people in general. It can cause it in men or in women in that case. Gliomas are forms of cancers that occur in the brain. And again, there is a brain cancer risk by using the phones close to the brain. So young adults are advised to use mobile phones for as short a time as possible, since their brain and eyes tissues are still in a formative stage and are consequently more vulnerable to the effects of radiation. I'm not trying to scare anybody, but just better be safe than sorry. Using text messaging and a phone with a low SAR, we define the SAR value are also recommended. When you buy your new phone, see if you can get one with a low value. Don't buy a cheap phone. Turning off the phone when not in use is also the most effective protection measure. To reduce the risks, the use of hands-free cellular phones is advisable. And that covers for us today both the ideas, the concept of stop sharing here of ionizing and non-ionizing radiation. I don't know why I lost the video here. I keep losing it. In any case, I'll still stay with the chat room for anybody who has questions. Please expect some assignments on the web page. And the class can be dismissed. Thank you, Alvaro.